In this lecture, we introduce the basic notion of Boolean algebra. And so we know what the algebra is in mathematics. So what is an algebra? So algebra consists of variables such as x, y, z. Okay, so each variable can contain a value, a real value, positive or negative or zero. Then we got the constants. The constant can be from minus infinite to plus infinite. So any number. E is a constant, and also can be others. E is also a number in the range above. Then we got operations. So operations can be plus, minus, times, then division, then sine, cosine, log, and so. It also has the functions. For example, function of x, if x is a variable, then it's an expression x squared plus x plus 1, something like that. Then we got expression. X plus y is an expression. X where x and y are variable, or x plus y plus 10 is also an expression. These four things together defines algebra. Now, so the Boolean algebra is a subset of algebra, or a particular version of algebra, where variables are the binary variables. So what is binary variables? Each variable, such as x, can consist 0 or 1. Y can consist 0 and 1. Okay, so every variable in Boolean algebra can consist either 0 or 1. Then the constants. So we do not have the infinite number of constants in this case. The constants can be 0 or 1. That's it. It can be 0 or 1. And then the operations. So operations can be the logic gates, or the logic logics. So how many logics we have studied? 7 logic, I believe. And logic, or logic, not logic. These 3 basic logic, and then we have 2 universal logic, NAND, NOR. We also have XOR, XNOR. This total 7 logic. These are the operations. Then after operations, we got functions. The functions consist of, let's consider f is a function, and this function is of 2 binary variables. And I know there's a function. It should be an expression like x square. No, so do we have the square operation in Boolean algebra? We do not have that. So we do not have that. So we can say a or y, right? It's a function. So now expression like x prime plus y plus xy plus z. So this is a typical expression. This expression can, the smaller expressions, the larger expressions, so different types of expressions. Okay, so now I believe the Boolean algebra is defined. So now in the regular algebra, we have some rules, such as a plus b whole square equals to a square plus 2ab plus b square. So similarly, in Boolean algebra, we also have the rules we call them the identity. So before starting the Boolean identities, let's try to explore the Boolean algebra by using an example. So we got the example here that write the truth table and draw the logic circuit. For a function of three variables a, b prime plus c. Okay, so now first we need to find the truth table. So it has three variables, and the truth table is the function f equals a, b prime plus c. And so how many combinations are possible for three variables? It's a 2 power 3, which is actually 8. So that's why we need 8 rows here to represent the truth table. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so now ab prime. So ab prime gives us 0. Okay, so we can do it directly. So if you are comfortable doing it directly, I'm fine. Or if you are not comfortable doing it directly, then you can go step by step. Okay, so since we are still in the beginning of the class, so we would like to go step by step. Okay, we don't want to go it directly. Okay, so in order to go so now, so we got a. Now, so we need to find b prime. Let's find b prime. So if b is 0, then b prime is 1 1 0 0 1 1 0 0. Then we need to find ab prime. ab prime. So 0 times 1 is 0. Again 0 0 again 0. It's 1 1 0 0. Now we need to find a b prime plus c. Okay, step by step. So now so a b prime plus c. Okay, a b prime 0 plus 0 0 0 plus 1 1 0 plus 0 0 0 plus 1 1 1 plus 0 1 1 plus 1 1 0 plus 0 0 0 plus 1 1. So that's the truth table of this function. So if you are comfortable doing this truth table directly from here to there, I'm fine with that. And you should be doing that. But I'm fine in either way. So now we want to we want to draw the logic circuit for that. So a, b prime plus c. So now we have actually three variables here. A, b, c. Three variables a, b, c. Now first a, then we got b prime. So in order to find the b prime, so we got the b prime here. Now a, b prime, we need an AND gate. One input is a, another input is b prime. So we got here a, b prime. Then plus c, we need an OR gate. And one input is a, b prime, and another input is c. So now we got the function, which is a, b prime plus c. So now we talk about the Boolean algebra rules, which are the Boolean algebra identity, the basic identities of the Boolean algebra. We have a total 8 identities. So it's the basic identities of Boolean algebra. We have 8. We know that we have 1 2 3 4 5 6 7 8. Okay, so now first we want to evaluate various operations, particularly two operations, and or. So where we have a variable and we have a constant. Let's consider A is a variable. A is a variable and the constants are 0. So now we want to see, so what is A plus 0? We want to see what is A times 0. We want to see what is A plus 1. We want to see what is A times 1. Okay, so now let's try the first one, A plus 0. So we got A and A can be 0 or 1, and then A plus 0. So 0 plus 0, 0. 0 plus 1, 1 plus 0 gives us 1. So now this one and that one are the same. So A equals A plus 0. So now we can conclude A plus 0 equals A. Similarly, if we want to find it for A times 0, then what do we get? We have A times 0. It can be 0, 1. So now 0 times 0, 0. And 1 times 0 is also 0. So whatever the value of A can be 0 or 1. But A times 0, it always gives us 0. A times A always gives us 0. Now we want to evaluate A plus 1. So we have A plus 1. A can be 0, 1. Then 0 plus 1, 1. 1 plus 1, 1. So A plus 1 is always 1. Then A times 1. A times 1. So 0 times 1, 0. 0 times 1 times 1, 1. So these two columns are same. So A equals A times 1. So if it is A times 1, then this equals to N. This equals to A. So these 4 rules we now know. So these 4 rules are between a variable and a constant. Now we want to know between the same variables. We want to know so what is A plus A? What is A times A? So now if we have A can be 0 or 1, and we know that A plus A, 0 plus 0, 0, 1 plus 1, 1. So A equals A plus A. So now we got A plus A equals A, the first thing. The second thing is what is A times A. Now if we have A and A times A, then what do we do? 0, 1. 0 times 0 equals 0. 1 times 1 equals 1. So we conclude that A times A is also A. Now the next identity is between a variable and its complement. So now if A is a variable and A prime it is complement, then we want to know A plus A prime, A times A prime. What are these? Okay, so now if we have A, then we have it can be 0, 1. Let's try to find A prime. Prime is 1, 0. So now A plus A prime, A plus A prime, what is that? A plus A prime, 0 plus 1, 1, 1 plus 0, 1. Okay, so A plus A prime is always 1. So now we can say A plus A prime is always 1. It's always 1. Now how about that? A times A prime. A times A prime. 0 times 1 is 0. 1 times 0 is 0. So A times A prime is always 0. That's the conclusion. And now, so if I ask you, so what is that? A prime. We already saw that somewhere in the previous lecture. And A prime is equals A. Then now, so we have four more identities. And the first identity among these four is called the commutative principle. Commutative principle. So the commutative principle is that A plus B equals B plus A. It means that order does not matter. So A plus B, B plus A. So in the truth table, we write A first or B first, doesn't matter. It will always give the same result. Then A times B equals B times A. These two identities are called the commutative principle. Then the next one is associative principle. The associative principle consists of three variables. It's considered A, B, C. Now A plus B plus C. We can apply a single operation at a time. But here in this expression we have two operations. One is between A and B and another between B and C. Now which operation we apply first? Doesn't matter. It's the same thing. So now if we apply the first operation, and then if we apply A plus B plus C, the next operation first, in the first expression, the first operation first, the second operation second. In the next expression, the second operation first, the first operation is second. So then these are actually the same. Thing. Now similarly, so we can do it, we can change it by for A, B, C for times. If we do this first or that first, doesn't matter, this will give us the same thing. It's for or, and it's for and. It's the same thing. Yeah. The seventh principle we call the distributive principle. Okay, let's create some space here. So the seventh one is the distributive. Now if we have A times B plus C, then we can distribute A in both B and C. This is actually AB plus AC. So we have A times not only with B but also with C. So now we are distributing A into B and into C. That's how we get AB plus AC. Now tell me, so if we have A plus BC, and what will be that? So now we have A plus B, A plus, and this plus is not for B but also for C. So now what is the relation between B and C? The relation between B and C is time relation. Now B and C is the time, and in B, so we are distributing A now. So the relation between A and BC is plus. So now we want to distribute A in B and also A in C, and the relation between A and BC H plus, so that's plus. And after doing that, we get this, and the relation between B and C each times the time. This is the distribution law. And the very last one is the De Morgan theorem. Also for De Morgan theorem, okay, let's do that there. The De Morgan theorem is there. Is A plus B whole prime equals A prime B prime. That's the De Morgan theorem, the first De Morgan theorem. Now if we do it for the, this is for plus and this is for and. As for or, the first one is for or, the second one is for and. So A B prime, this will be as the relation here, the A times. So now this will be plus A prime B prime, A prime A prime plus B prime. Okay, this two are called the De Morgan theorem. Now so if we are asked to prove any of the identities that we have studied by using truth table, then we should be doing that. So for example, prove the distributive principle using truth table. So what is the distributive principle? We know that. So there are two forms of the distributive principle. The first form is A times B plus C equals to AB plus AC. Now if we have the truth table AB, okay, so now we want to find the first expression, the left hand side expression, and the right hand side expression, and we want to see the left hand side expression and the right hand side expression give the same thing, give the same column. It's 0 0 0 1 1 0 1 1. We got A. Now let's find A plus B, B plus C. So we actually need another variable here, C. So this is actually not right. That's not right. We need to redraw the truth table. We actually have A, B, C, not only A, B. So it should have here 8 combinations. 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. This is too tight. Now we want to find B plus C. What is that? It's B plus C 0 1 1 1 0 1 1 1. Then A times B plus C. A times B plus C, what will be that? A times is 0 0 0 0. Then B plus C is 0 1 1 1. Now for the right hand side, we want to find AB first, AB. Then we want to find AC. Then finally we want to find AB plus AC. So now AB is 0 0 0 0, and again for 0, 0, 1, 1. For AC, 0, 0, 0, 0. Then here AC, 0, 1, 0, 1, 0, 1, 0, 1. Now AB plus AC, 0, 0, 0, 0, 0, 1, 1, 1. So now if we compare this column with that column, and we see that A times B plus C equals AB plus AC. So this distribution principle is proved. Now if we want to prove the second distribution principle, then let's do it in the same way, in the similar way. The second distributive principle is A plus B C equals to A plus B times A plus C. Okay, so we want to find the truth table. Now we have 3 variables. Okay, we should have 8 options. 4, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now first we want to find the first expression, A plus BC, and we already have A. Let's find BC. 0, 0, 0, 1, 0, 0, 0, 1. A plus BC, 0, 0, 0, 1, then 1, 1, 1, 1. Okay, we got the left hand expression. Now we want to find the right hand expression, and first we find A plus B, then we find A plus C, then we find A plus BC. See if we can show sorry, this A plus B times A plus C. If we can show that the third column is and the sixth column are the same, then this identity is proved. So for A plus B, 0, 1, 0, 1, 1, 1, 1, 1. For A plus B. Oh, okay, actually. For A plus B is A plus B. So first one is 0. The second one is also 0. The second one is 0. The third one is 1. Okay, now it's right. For A plus C, that's 0, 1, 0, 1, 1, 1, 1, 1. Now A plus B times A plus C is 0, 0, 0, 1, 1, 1, 1, 1. So now if we compare that column with that column, then these two columns are the same. So we prove the second identity of the distributive principle. So in the same way, we should be able to prove the commutative principle, the associative principle, and also the De Morgan theorems. Note that for each of the identity there are two forms, one form for AND logic and another form for OR logic. Now so we try to explore how to use these 8 basic identities of Boolean algebra in practice. for simplifying expressions. Let's see it by using a couple examples. The first example that we have, draw the logic circuit for a function. Okay, so draw the logic circuit. Logic circuit for a plus b, a plus cd. So how many variables we have? A, B, C, D. So 4 variables. Then simplify this expression by using the basic identities of Boolean algebra and draw the logic circuit for the simplified expression. Then we'll see how many gates are minimized. Simplify. Draw again. And then how many minimized? How many gates are minimized? So for drawing that, so we have 4 variables, A, B, C, D. And for A plus B, we need an OR gate. For CD, we need an AND gate. So that's the A plus B. This output is CD. And for A plus CD, we need an OR gate. And the first input is A. Okay, let's try to find A from there. A. And the second input is CD. So now we got here A plus CD. Now the relation between A plus B and A plus CD is AND. So we need another AND gate here. Now, so the outcome, we get A plus B times C plus D. Now we want to simplify this expression by using the identities. So what is the expression that we have? So we have A plus B times A plus CD. Let's simplify it. Let's use the distributive principle, and for that we have A plus B times A plus B times CD. So we have used the distributive principle. Okay, so you need to mention that. Then we again use the distributive principle here. We have AA plus AB plus ACD plus BCD. So again the distributive principle, you need to mention that. Now we know that A times A equals A plus AB plus ACD plus BCD. Okay, so now we need space. Let's create some space. Now, so we have it. Well, so now again the distributive principle, if A, then 1 plus B plus ACD plus BCD. We know that 1 plus B equals 1, then A times 1 equals 1, or A times 1 equals A. So we got A plus ACD plus BCD. Well, we again need space. Then we want to create more spaces here. So then we got we again apply the distributive principle. Then 1 plus CD plus BCD. Then 1 plus CD is 1, or 1 plus anything equals 1. Then this is 1, and A times 1 equals A. So A plus B C D. So this is the simplified expression. Now we want to draw this. we want to draw the corresponding logic circuit. For doing so, so we got the equation here, we got the expression, and we want to draw. So now we have 4 inputs, definitely A, B, C, D. A, we got direct A, then B, C, D. We need an AND gate of 3 inputs AND gate, and this outcome will give us B, C, D. Then an OR gate, 2 input OR gate. The first input is A, and the second input is B, C, D. So that's how we get here A plus B, C, D. So now the first circuit and the second circuit are equivalent, or the functionality of both of the circuits are the same. The outputs are the same. So in order to draw the first circuit, we need 1, 2, 3, 4 gates, and for the second one we need 2 gates. So if you are asked how many gates are minimized, 2 gates. In this case only 2 gates, but in real case, so where there are billions of gates, if 50% are minimized, then this is a lot. If a circuit has 4 billion gates and a simplified circuit has 2 billion gates, then 2 billion gates are minimized. This is huge in practice. Now let's see another example. We want to simplify a function again, and the function that we are given is f equals a prime bc plus a prime bc prime plus ac. Now if we want to draw this logic circuit, then how do we do? So A, B, C. So we actually have 3 inputs, A, B, and C. And we need A prime, so we need an inverter, which is A, B, C. Then we got A prime. Okay, so then so we need BC and AND gate 1, 2 is BC. A prime BC, so another AND gate. Or for simplicity, we can actually use a 3 inputs AND gate. We don't need 2 AND gates. We can use a 3 input AND gate. The first input is A prime, the second input is B, third input is C. Now then, for the second expression, so we need A prime. We already have A prime. We already have B. We need C prime. So we need an inverter, and we got here C prime. This output is A prime B C. Now for the second expression, we need another AND gate. Again, 3 input AND gate, A prime. So do we have A prime? Yes, we have A prime here. A prime, then BC. So why do we have B? Well, we got B here, B, and then C prime. This output is A prime B C prime. Then for AC, we need another AND gate of 2 inputs. The first input is A. Let's bring A there, and the second input is C. So the outcome is A C. Now we got A prime BC, we got A prime BC prime, we got AC. Now we need a OR, three input OR gate. So in the first input, the second input, and the third input. Okay, that's how it will give us the function of 3 variables. So how many gates we have needed? 1, 2, 3, 4, 5, 6 gates. Okay, 6 gates. And let's store the number. We want to simplify the function by using the basic identities of Boolean algebra, and then we'll draw the function and we'll see so how many gates are minimized. Also, for doing the simplification, so what can we do? So we now simplify this function by using the basic identities. So can we apply the distributive principle here? I think so. Yeah, it's a prime b is actually in both of the terms. So now if we got a prime b from both of the terms, then we got c plus c prime and plus ac. Okay, so now a prime b, c plus c prime, we know is 1 plus ac. Now a prime b times 1, anything times 1 equals anything. A times 1 equals a. A prime b times 1 equals a prime b plus ac. Can we simplify it more? A prime b plus ac, distributive, no. Associative, commutative, De Morgan, no. Okay, I think this is the simplified one, and we want to draw the circuit now. Each of 3 variables a, b, c. We need a prime, then we need an inverter. It will give us a prime. Then we need a prime b, so we need on AND gate. Yes, a prime b. Then we need a c, ac. The first input is a, second input is c. So now we got here a, c, and we need an OR gate of 3 inputs, or gate of 2 inputs, sorry, and the output will be a prime b plus ac. So now, so how many we have needed here? 1, 2, 3, 4 gates. So in the previous version we needed 6 gates. Now we need 4 gates, and we actually have minimized by 2 gates. Now so we got another example here for the similar task. The function that we have is of 2 variables equals a plus a prime b. So for drawing this function, so what can we do? So we have 2 inputs, a, b, and so we got a, we need a prime, so we need an inverter, and it will give us a prime. Then we a prime b, so we need an AND gate, a prime and b, so this will give us a prime b. Now a plus a prime b, so we actually need an OR gate, and the first input is a, and the second input is a prime b. So this is a plus a prime b. Yeah, now we want to simplify it. The function that we are given a plus a prime b, and we want to simplify it. What can we do? De Morgan theorem, no. Commutative, no. Associative, distributive. Is there any way of doing distributive here, applying distributive? Yeah, the second identity of the distributive principle, the second identity, each of the principle has 2 identities, 2 form, one for AND gate, AND logic, and another for OR logic. So now if we want to use the distributive here, then we get a plus a prime times a plus b. We know that a plus a prime, so put it here, distributive. So a plus a prime equals 1 times a plus b. The 1 times a plus b equals a plus b. So that's, I believe, the simplified. And for doing so, for writing for drawing this circuit, so we need an OR gate, simple OR gate, and two inputs are A, B. That's A plus B. So we needed 1, 2, 3 gates, and in the simplified one we need one gate, so two gates are minimized. Thank you.